Today, we are finally going to find the equation of a tangent line to a surface. It only took us till November to get here, but better late than never. All right, so we've got our function here. We did this as an example in section 12.6, sine x times cosine y. And the example I did in the video, we were given a point in R2, pi over 3 comma pi over 3. And that point is, only two coordinates, so it's down in the xy plane. All right, and we said that the directional derivative that we calculated would go up to the surface, to the point that's actually on the surface above that point. And we were given a vector, a directional vector in R2, all right? And the directional derivative that we calculated was all about that tangent line. So we turned on that tangent line and it said, if I go 1 unit in the direction u, how much do I have to go in the z direction to get back on the line? So we went 1 unit in the u direction, and then we had calculated, let's see, we had to go 13 over 20 units in the z direction to stay on the line. All right, so today we're going to find the equation of the line that is tangent to the surface. And remember what we need in R3 to find the equations, the parametric equations of a line. We need a point, which is going to be this point B, and we need a direction vector. Okay, well, that direction vector is just going to be the x component and the y component of that u vector that we were given. And then the z component is just going to come from that directional derivative that we already know how to calculate. All right, this slide has a lot on it. Let's see if we can make sense of it. It says that the tangent line to a function in two variables, f of x, y, in the direction u equals ab at x naught, y naught, is the line through a lot of symbols with a direction vector, even more symbols. Okay, let's dissect what we've got here. All right, so you are going to be given in these problems the function f of x, y. Okay, so this is going to be given to you, and they're going to give you the direction vector u. That's a vector in R2. That's the one sitting down in the plane, the same one that we had in section 12.6. And you're also going to be given the x and y coordinates of a point down in the xy plane. All right, so what you're going to figure out is just the point and the direction vector for that line that's out in R3. Okay, so you're going to take the x naught, y naught from the point that you were given over on the left, and you're just going to find the z coordinate of it. You're just plugging that into the function that they give you. So this is just a point in R3. We're going to calculate the point in R3. So we have the point in R3, and now we need the direction vector. The direction vector is going to steal its x and y components from the given unit vector. So we're just going to steal those x and y components for free. And then the z component of the direction vector is going to be that directional derivative that we learned how to calculate in section 12.6. Just a couple of reminders that that direction vector has to be a unit vector. So if it doesn't start that way, we'll have to make it that way. And also just a reminder of what our directional derivative formula is. It's the gradient vector dotted with that unit vector. All right, so let's give this a try. We're going to find the parametric equations of the line tangent to this surface at the point 2, 1 in the direction of 3, 4. All right, so the information that we're given is not just the function, but we're given a point and a direction vector. So the point that we're given is this x naught, y naught, the 2, 1, and the direction vector would be AB if it was a unit vector. So the first thing I need to do is to take this direction vector 3, 4 and make it a unit vector. So let's do that off to the side here. Our unit vector is going to be the vector 3, 4. I keep picking these numbers because they make a nice Pythagorean triple when I divide by the magnitude. 3 squared gives me 9, 4 squared gives me 16, which is the square root of 25. So I'm dividing by 5. So my unit vector is going to be 3/5, 4/5. So the two things that we need in R3 for the parametric equations of a line are the point and the direction vector. So the point is already almost completely done for us. So we have the point, which is going to be the x naught, y naught, so the 2, 1, and we just need to find the z coordinate. The z coordinate is just the function value at 2, 1. So we're going to plug in f of 2, 1, just finding function values. So let's go up to our function given in the problem, negative x squared y, so negative 2 squared times 1, plugging in an 2 wherever I see an x, and a 1 wherever I see a y, plus xy at the end is going to be 2 times 1. And let's see, I've got negative 4 plus 2 plus 2. That's a whole lot of nothing. So my z coordinate of my point is 2, 1, 0. Right, so the other thing we need is our direction vector. All right, so our direction vector for the line, you're going to get your x and y components from the direction vector of our unit vector u that we calculated in blue over there on the left. So we're going to have 3/5, 4/5, and then we're going to have to calculate a directional derivative to get the z component. All right, so I'm going to have to find that directional derivative. Remember that the directional derivative is the gradient dotted with the unit vector. So the first thing I'm going to do is calculate my gradient. All right, so our gradient comes from taking the partial of f with respect to x. So back up to my function. With respect to x, I'm going to get negative 2xy, treating y like a constant, plus, see, derivative of x times y squared. Y is just a constant, so we'll just get the y squared constant. And then derivative of x times y with respect to x is just going to be y. Then do the same thing, derivative with respect to y. So now the x is the constant. Derivative of negative x squared y is going to be negative x squared. Derivative of xy squared is going to be x times 2y, or 2xy. And derivative of xy with respect to y is going to be x. Lots of y's and x's. All right, so we're going to dot that with the unit vector to get the directional derivative. But first we want to figure out the gradient at the point we're interested in. So we're going to find the gradient of 2, 1. So negative, everywhere there's an x, put a 2. Everywhere there's a y, put a 1. And see what we get. All right, so I got negative 4 plus 1 plus 1, negative 4 plus 4 plus 2, and we get negative 2 and 2. That's not so bad. That's my gradient vector. All right, so my directional derivative in the direction of u at that point is going to be my gradient dotted with the unit vector. So my gradient was negative 2, 2. Dotted with that unit vector. And let's see, when I multiply 3/5 times 2, or negative 2, I get negative 6/5. Multiply and add. 2 times 4/5 will give me 8/5. And I get 2/5. So all that work was to get the z component of my direction vector. All right, so that's the 2/5. That's going to go here. Plug that in, 2/5. All right, let's clear off this slide because I have no more room to find the equations of the line. All right, we've calculated the point on our line. We've calculated the direction vector of our line. Remember how to find the parametric equations of a line. All right, they all have that constant term that comes from the point. So x is 2, y is 1, z is 0. And then the direction vector is always the coefficients of the t parameter. So we're going to have plus 3/5 t plus 4/5 t plus 2/5 t. All right, so we could delete that 0, but we get the idea. All right, so let's go graph this in GeoGebra and get some satisfaction with it. All right, so here's our surface in R3 graphed, and we were given the point 2, 1, and we found that the z coordinate was 0. We were given the direction vector 3, 4, so that's in this direction here, and we wanted to find the equation of the tangent line, and here's what we found. Got my parametric equations in there, and thankfully that looks like it's hitting that at a perfect tangent, and it's in the right direction. If I look at bird's eye view, that line lines up completely with the direction vector that we were given.